Hi everybody, this is Salvatore Sanfilippo, and today for Dev's Lunchbox I want to talk to you about an algorithm, which is an optimization algorithm that is called simulated annealing. Annealing is a physical process where you have some steel or other metal, and this metal you want to basically raise the temperature and then cool it down very slowly in order for the crystalline structure inside the metal to become stronger and fix small faults that you can have inside. And this algorithm was constructed basically as a simulation of this physical process in terms of numerical problems that we want to optimize. So, for example, imagine to have something like that. So what is an optimization algorithm and what is its goal? It is to find the value of a set of parameters in order to optimize some function. In simulated annealing, this function that we want to optimize is called usually the loss function, which is a measure of how bad the solution is performing, its loss. In genetic algorithms that you may know, normally instead we want to optimize the fitness function. That is exactly the contrary. The greater the fitness, the best the solution is. So for example, in this case, I want to optimize a single parameter, which is the x-coordinate, which is along this line, where I want to throw a ball, and I want the ball to reach the lowest point possible in all this curve. Of course, the best is here. This is our best solution, and it's where our loss function has the smallest value. However, there are many local minima. For example, this is a local minima. It's if you see if you zoom in this part of the problem space, it looks like to be optimal, but if you have a greatest vision of all the problem space, you see that here it's much better compared to in this local minimum. So in the simulated annealing algorithm, there is a very important parameter, which is T, and this is the temperature of the system. You start with a given temperature, for example 100 or whatever, and then this temperature will go down towards 0. And as this happens, different things happen. For example, here my only parameter is basically the x-coordinate of where I launch my ball. I can start here, for example, and given that temperature initially is very high, I am allowed to do big jumps in order to explore other possibilities. So, for example, here the loss function is the altitude. The greater the altitude, the worse the solution, because I want to find the place in my hills which is basically the lower. So here there is a 50 meter altitude. So this is my current value. I can try, given this solution, what a simulated algorithm does is to perturbate this solution. For example, adding plus or minus random, which is function of the current temperature. So the greatest temperature, the biggest change I will make to the current solution in order to create the next candidate. So for example, I modify a bit this, and I try here. And actually this is just, for example, I don't know, 45 meters. And it's a better solution. However, how do I accept this solution as better than the previous one. If I only accept solutions that have where the current error of the perturbated solution is smaller than the past error, what happens is that I will accept that, then I will try other stuff and I accept that and I accept that, and finally I find the local best solution, so it's a local minima. However, I want to be able to go here in order to find the truly best solution of my parameter. In order to do so, what simulated annealing does is to accept even a bad solution with a given probability. So the probability of accepting a worse solution compared to the current one is p. Normally, this formula is used exponential function of minus delta divided by the current temperature. The minus delta is basically the difference between the current error and the past error. Okay, so basically what simulated annealing will do is, if the new perturbated solution is better than the past one, I accept it always. However, if the new solution is worse than the past one, I may accept it using this probability here. Basically, with this exponential function towards negative numbers, it means that the greater is the error here, the greater the error, the less likely is that I accept a solution that is worse than the current one. The greater is the temperature, the more likely I am to accept a worse solution. So initially, basically, I can accept bad solutions compared to the previous one without many problems. As the temperature is cooling down, I will accept mostly only better solutions. So this means that as I perturbate, sometimes I go here and I accept the solution, and then I go here and then I perturbate again, I go here, and finally I will go here, because this is called yield climbing. I will climb the yield because I am willing to accept when the temperature is very high a worse solution, so I can go over my local minima and find a better space of the solution. Then, as the temperature is cooling down, I start to do smaller jumps. Sometimes I still accept a worse solution, but then the solution will very likely converge to the best possible solution here. This is the basic algorithm. We can check it here. Yes, so we start with the parameter T, which is the initial temperature. Then our current solution is initially a solution generated at random. And my initial cost function is pure infinite. So I will accept for sure a new solution in the first iteration. While the temperature is greater than 0, I create a new solution perturbating the past solution. How it is the perturbation process performed? Well, it's easy. Normally, if you have numerical parameters, you just add or subtract from the random number, which is proportional to the current temperature. If you have other problems, the perturbation may consist in rearranging the items that you have, if there is an order in this item, if you are finding are looking to find the best order among something. And of course you will permute more aggressively when the temperature is high, and less aggressively when the temperature is low. Then we calculate this loss function. Loss is the loss function of S, the current solution. If the current solution is I mean, if the past solution, which is the current loss, is greater than the loss of the perturbated solution, I accept the new solution because it's better than the past one. Otherwise, I calculate this delta, which is the difference between how worse is the perturbated solution compared to my previous solution, and then calculate the probability P of accepting a new solution. And then if P, and then I throw a number between 0 and 1, and at this point, if my random number R is if my probability is greater than my random number here, I accept this solution. And here I have to also update C to loss. Okay. And then I calculate the next temperature. How it is the next temperature calculated? Here I used a function, but normally this will be like T equal T times alpha, and alpha will be like, for example, 0.95. So I reduce the temperature in an exponential way. However, also it is possible to have a linear change of the temperature. There are many different scheduling possibilities for the temperature. So that's the basic algorithm. However, I want to show you something. Let's return here and clear the canvas. Sometimes it could happen that for some reason, maybe I was here, which is the best, but the temperature is still very high, and I go here, and because of the cooling temperature schedule is too fast, I don't have time to return back to the optimal solution. So it is very interesting to update our algorithm, always tracking the best ever solution that I found so far. So after every given number of cycles, so my temperature is decreasing, if my current solution is worse than the best ever solution, sometimes I do some kind of backtracing and I jump back to the best solution that I found. So at some point I say okay, yeah, this is not going to work because I had a better solution here, and I jump back at a lower temperature this time, and I continue the process, and I will find the local minimum. So basically, the algorithm is updated having a best candidate. Initially will be just null, and then I have also a CB, which is the loss function of the best current solution, and then I can update this best solution and after some cycle restore it. It's a simple change to the algorithm. Many years ago, I wrote a program which is called Shape Me. This is a very classical problem that circulated a lot many years ago, and it's a program that, given an image, this is the Annunziata of Antonello da Messina, Sicilian painter, given a given image, find a set of triangles that will approximate this image as best as possible. So I want to evolve this. This is the binary file, and then there is also an SVG output. And I want to do it with max shapes 64 triangles, maybe, initial shapes, and start with 64 triangles. Okay, the first solution is completely random, okay? And you can see here the temperature decreasing, as you can see, and this is the generation number, and this is the difference, this is the error, our loss function. The loss function is defined as the difference between the image and the current solution that I have. Basically, every pixel is considered as a point in the space RGB, and it performs the difference between this pixel and the other pixel that I have in the other image, and the sum of all the differences is our loss function. The average of the difference of all the pixels are our loss function. As you can see, the algorithm sometimes go back to worse solutions compared to what it found, and then it returns back. This algorithm implements this absolute best idea, and after some time it will restore the best algorithm. So we can continue here to see things about our algorithm while having at the same time this window here to see how the evolution will go. So another classic thing that you can do with simulated annealing is to solve the traveling salesman problem. So you have a set of points, and you want to find what is the sequence to visit them in order to have the shortest path. So this is probably something like that, you know, but this is an NP complete problem, so it's very hard. So basically every vertex here will have a number, and you can imagine this as your current solution. Just you start with a random array of the numbers, and the perturbation is swapping them. So my first solution can be like, I don't know, 5, 4, 5, 1, 2, 6, and so forth. And when I perturbate, I exchange elements, and as the temperature T is higher, I use farthest swaps, and I perform more swaps for every iteration, and as the temperature is cooling down, I start to do just one swap at the end, and maybe just very near elements. So my initial solution is totally garbage, and then as the temperature decreases and I try more and more solution, I am able to approximate the best solution that I found in the past. Another very, very interesting thing, let's see if, our triangles are evolving into something which is much more meaningful compared to the past. Another interesting thing about simulated annealing is that it can be used in order to evolve neural networks in situations where we cannot use gradient descent algorithm, because in order to use the gradient we need to have a training set and we have to estimate the error. Instead, what we can do here is, for example, I have this small car here. Basically, I want this car, which implements a neural network inside. Here there is a neural network, and it needs to be able to drive here. And the output of the neural network will be the steering, like left or right, the acceleration, for example, and the input of the neural network will be maybe the current heading, the current velocity, and also some array like of pixels where every pixel, it's like if it could see what's in front of the car, and every pixel is the distance between before the wall. Okay, so I can start with a random neural network. This is our neural network. It's maybe just a fully connected network here, and here I assign random weights here. And in this case, using simulated annealing, I can train the network without having a training set, but just using the loss function of the amount of path, the length that the car is able to drive before crashing. So, for example, my first neural network will just crash immediately. So we'll have just a loss function which is just maybe, okay, if the wall path is 100 meters, I can do 100 minus the distance that it was able to travel. So my loss function will be 97 because it was able to perform only 3 meters. Okay? Then I perturbate it and try it again. And this time maybe we'll drive a bit more, and so far and so forth. And I will end basically with a set of weights that are able to drive for all the distance. I can make my loss function more interesting and also put the velocity also as the input of the loss function. So the car that is able to travel the wall distance faster will win over another one that is able to still perform maybe all the circuit but at a lower speed, and so forth. And that's very interesting as well. Normally this problem is also solved using genetic algorithms. Okay, at this point, using 64 shapes, our Annunziata starts to be recognizable. One thing that you may ask yourself is what is the difference between genetic algorithms and simulated annealing? Because if you know genetic algorithms, probably you understand that there is some similarity. Well, this is GA is a population-based algorithm for optimization, and this is a single solution algorithm where we perturbate again and again the same solution. Let's say that GA could be more useful when the set of solutions contains many solutions that are very good. And instead, SA could be more suited when we have a single optimal solution in the problem space. But in general, you can also mix the two algorithms, and it was performed many times in different research papers. For example, you can evolve using GA. You have a generation. Before evaluating who will be basically the parents of the next generation offsprings, you perform a pass of SA, simulated annealing, on the current solutions that we have in the generation of genetic algorithms, in order to find the better versions that you can in a couple of iterations of what you obtained, and then select the best two after evolving them a bit with SA. And this could be an improvement. It was used in the past, and many variations. Also, a couple of things about the temperature. There are many temperature schedules. Basically, the idea of lowering the temperature, as we say, always from the very high to the very low, it's important when you don't have this change that I suggested to the algorithm, which is when you don't have the very best solution saved. If you always save the absolute best solution that you found so far, you can also experiment with different cooling schedules. For example, you go to zero, and then you start to rise and lower the temperature in order to find to escape other local minima of certain parameters. Because anyway, you don't have problems going back to a worse solution for a moment, because anyway, the absolute best solution you always saved. Okay, well, that's all. I hope you enjoyed this Dev's Lunchbox episode, and thanks for watching. Bye.